Swayam Prabha. Digital India. Educated India.
Good morning. Today we start our module on complex analysis. We start with analytic functions. We define the function of a complex variable z as a rule which will associate a unique complex number like this for every z in a domain in the z plane. And as for any calculus, that is, for example, calculus of real functions, we start with the definition of limit, continuity and derivatives. The first, limit. If the function f of z is defined in a neighborhood of a point z0 except possibly at z0 itself, what it means is that for the definition of the limit at point z0, it is not necessary for the function to be defined at that point. You can define a limit without the function being defined at that point. So, if the function is defined in a neighborhood everywhere in a neighborhood of z0 except possibly at z0 itself, and if there is a complex number I such that for every epsilon, every positive epsilon, whatever small, you can find a delta such that taking the point z in a delta neighborhood will keep the difference of the function value from the value I within an epsilon neighborhood, then we say that limit exists. That is, around z0 you can find a small neighborhood such that you can approach the function value as I with any tolerance required. Whatever tolerance you want, accordingly you would ask for the delta neighborhood to be closer and closer. If you can achieve this, then we say that the function has a limit at z0 and that value I is the corresponding limit. Now, this limit can be defined even if the function f is not defined at z0, that is, at z0 even if the function does not have a value associated with it, and even if the function has a value associated with it at z0, but the function value is not I, but along every path, if this I value is achieved, is approached rather than achieved, even then we say that I is the limit. That means, the function value at that point and the limit at that point may be different, as in the function of real variable as well. Now, here you will note that there is a very important difference with real functions. In the case of real functions of a single variable x, the point x0 could be approached only along one direction, from the left or from the right, of course. So, x0, point x0 could be reached either from x0 minus delta or x0 plus delta, left side and right side. But in the case of complex variable, the description of the variable is not along a line, but on a plane, and therefore, there are infinite directions along which the point can be approached. And this is the crucial difference which makes the definition of the limit in the case of a complex function much more restrictive. That is, it is not enough for the limit to be same along two directions mutually opposite, but along all paths in the complex plane. So, all paths leading to the point z0 should give us the same limit, and in that case we will say same limit I. In that case we will say that limit exists and that limit is I. Now, this makes it extremely restrictive definition, and apart from that, if the value of the limit and the value of the function also at that point is same, then we say that the function is continuous at that point. That is, the function should be defined at that point and limit should exist in this sense, and the function value and the limit must be same. In that case, we say that at z equal to z0 the function is continuous. And continuity in a domain means continuity at every point of the domain. Now, after defining limit and continuity, at the next step we define differentiability and the derivative. So, just like real calculus, we make the first steps in the definition of the derivative of a complex function, and that is from z0, if we take a small difference and reach the point z, then this is the difference of the values of the function at the 2 points, and this is the difference of the 2 values of z. Now, this limit as z tends to z0 will give us the derivative if this limit exists, right. So, as z tends to z0, if we show z as z0 plus delta z, then it will look like this. Now, when this limit exists, that means along all paths in the z plane, as z0 is approached is made closer and closer to 0, that means as the point z approaches z0 along all paths, then if all the limits turn out to be same, then we say that this limit exists, and correspondingly we say that f z is differentiable, and that value of that limit is called the derivative at z equal to z0. This again is extremely restrictive definition. That means that for a complex function of a complex variable to be differentiable, it must be extremely nice. That is, it has to satisfy such a restrictive requirement, and that within itself brings in a lot of desirable properties to the function. So, in that case, we find that the function that we are talking about, just by being differentiable, it brings in a lot of additional properties. All of them together is the concept of analyticity. So, we call a function analytic in a domain D if it is defined and differentiable at all points in D. If there is a domain in which at every point a function is defined and is differentiable in this sense, then we say that the function is analytic. And it can be shown that the function being analytic at that point means that it can be expanded in an infinite series of powers of z. That can be shown. And now, there are a few points which can be said in continuation of this set of nice properties that are brought in, and these are points which will be established or settled later as we study the integration also. So, one is that if we can establish that a function is analytic at a point, that means it is differentiable at a point, then that will also imply that the derivative itself also will be analytic. That means, it will possess a derivative of its own, and then by continuing on this argument, we can show that an analytic function will possess derivatives of all orders. And that means that in the case of the real valued functions, differentiability did not mean too much. A function could be differentiable once, but that would not mean immediately that the derivative itself will be differentiable. Now, in the case of complex functions, the existence of the first derivative itself requires so much that once the first derivative is established, then it implies a lot of other things, which will finally mean that once the function is differentiable, then it will be differentiable as many times as you need, and that is the entire implication of analyticity. So, this is the great qualitative difference between functions of a real variable and those of a complex variable. When we were studying series solution, at that stage, when we were talking about the coefficient functions being analytic at a point, the sense was this analyticity, that is, it is not only differentiable, but it has derivatives of all order, and that means that it can be expanded in a power series around that point, and that will be convergent. Now, there are a pair of conditions called Cauchy-Riemann conditions, which are satisfied by a function if it at a point, if at that point it is analytic. And to appreciate that, we consider this situation. Suppose a function f u plus I v is analytic, then we have f prime, which is limit of delta f by delta z as delta z tends to 0. Now, since z is x plus I y, so delta z will be delta x plus I delta y. So, delta z tending to 0 will mean both delta x and delta y tending to 0, and this is delta f from here, and this is the corresponding delta z. Now, if the function is analytic, then it will mean that the limit of this along all paths should be same. That means, for example, suppose this is a point z0, then 1, 2, 3, 4, 5 along all paths the point is approached, the limit is same. In particular, let us consider these two paths, horizontal and vertical. In the horizontal case, delta z is equal to delta x, because y does not change, and in the case of the vertical path, delta z will mean I delta y, because because x does not change. Now, if all these limits are same, then in particular these two limits also will be same. Now, as we consider delta z along this path, then delta z is delta x. So, this limit immediately will be del u by del x plus I del v by del x, that is this. If we consider this path, then delta z will be I delta y. So, keep the I delta y here. So, this will be 1 by I del u by del y, that is this 1 by I, which is minus I, because minus I square is 1, plus I by I will go out, will get cancelled, the rest is del v by del y, that is here. So, along this path we will have this derivative expression, along this path we will have this derivative expression. Now, from analyticity we know that along all these paths the limit is same. So, in particular along these two paths the limit is same. So, we get two expressions for the derivative, and as we equate these two expressions and separate out real and imaginary parts, then we get del u by del x is equal to del v by del y, and del v by del x is equal to minus del u by del y. These two conditions are called Cauchy-Riemann conditions or CR conditions or CR equations. So, Cauchy-Riemann conditions are simply this, and in this derivation we first assumed that the function is analytic at z0, and then we found that these two should hold at z0. That means that these are the Cauchy-Riemann conditions are necessary for analyticity of the function at that point. Immediately the second question that will arise, that are they sufficient also? That is, do the Cauchy-Riemann conditions imply analyticity? Answer turns out to be yes, and to establish that we consider two functions u and v, which have first order continuous partial differential coefficients, and these conditions among those partial derivatives hold, that is Cauchy-Riemann conditions hold. Then we want to show that the function is analytic. For that we construct delta u and delta v. So, what is delta u? Delta u will be u at the changed point minus u at the current point, and up to first order we will get this as delta x into del u by del x at the point x1 y1 plus delta y into del u by del y at the point x1 y1, right. what is x1 y1 here? X1 y1 is a point in the line segment joining the original point to the changed point, right. This is by mean value theorem. So, that means that by mean value theorem, and that is why we could use this equality without any plus dot dot dot, because we are not including the second order terms. So, that is why we have to use the mean value theorem and the remainder form of the Taylor series, that is remainder form of the Taylor's theorem. So, we are keeping only the first order change. So, we use the mean value theorem up to the first order, now which is Lagrange's theorem for that matter. So, this x1 y1 is a point which is in the line segment joining xy to x plus delta x, y plus delta y. That means, for a xi in 0 to 1, x1 is this and y1 is this. Now, this gives us the expression for delta u. Similarly, we get the expression for delta v, that is v at the changed point minus v at the original point. So, that gives us this expression for x2 y2 being a point joining a point on the line segment joining this point to that point. Now, x1 y1 and x2 y2 can be two different points, that is xy is here, x plus delta x, y plus delta y is here. As we join these two, we get this line segment, and x1 y1 could be somewhere on this line segment, x2 y2 could be somewhere on this line segment, need not be at the same point, maybe at different points. So, now this delta u and this delta v we have got in hand. So, what will be the corresponding delta f? That will be delta u plus I into delta v, that is this. We take this and add to that I times this. Okay. So, as we do that, we club together appropriate terms. This plus I into this you will find here, plus this into I into this you will find here. Now, an I has been kept outside, and that is why in this case we in this case this plus 1 we replace with minus I square. Okay. So, that is why this term has come here, I into this. So, I is outside, this is sitting here, and this is minus I square into this, minus I square is 1. So, out of minus I square, 1 I is outside, the rest of it minus I, and this whole thing is here. Now, we try to simplify this. For simplification, consider this if Cauchy-Riemann conditions hold, which is part of the hypothesis here. If Cauchy-Riemann conditions hold, then del v by del y can be replaced with del u by del x. Here already del u by del x is there, we will find del u by del x here also. Okay. So, then this first bracketed term you will find here. So, the del v by del y there has been represented with del u by del x. Similarly, here in this case we find del u by del y here, which can be replaced with minus del v by del x. Okay. So, as we replace this del u by del y here with minus del v by del x, this minus will become plus and we will have del v by del x here, that is this whole thing, that is this bracketed term, right. Now, we concentrate on this. This is del u by del x, this is also del u by del x. Now, we note that this is at x1 y1 and this is at x2 y2. If this is also, if this were also at x1 y1, then this whole thing we could have taken common, and what would come inside? Delta x plus I delta y, that is delta z. Okay. So, what we can do is that for the time being here in place of x2 y2 we take x1 y1, and that will mean that this term will remain and from there remain outside, and from there we will subtract this same thing with x1 y1 here. That means, I delta y del u by del x at x1 y1 we add and subtract, add to this and subtract from here. Okay. As we do this, we get the next expression in the process of simplification. Now, from here if we add I delta y del u by del x x1 y1 to this term, then this will come common, and along with that we will get delta x plus I delta y, and that you get here, right. Now, then whatever we added here, I delta y del u by del x at x1 y1, that same thing we subtract from here, and for that we will get common I delta y, and inside the bracket we will get del u by del x at x2 y2 minus del u by del x at x1 y1. That is the term here. A similar exercise we do on this. Here you see I del v by del x x1 y1, okay, and here there is a little mistake. Let me make a small correction. Delta y is missing here. Delta y is missing here. Now, here we have I delta y del v by del x x1 y1, okay, del I del v by I delta y del v by del x, okay, and outside there is another I, okay. So, I delta y del v by del x at x1 y1, and along with that we would like to have delta x into del v by del x at x1 y1. So, that we add to this and we will subtract from here, okay. As we add to this, we get the I common outside as it is already there, del v by del x at x1 y1 we take common, and then we get in bracket delta x plus I delta y, that is here, and whatever we added to this, that we subtract from here, okay. So, we added delta x del v by del x at x1 y1. So, that same thing we subtract from here, and then the result is here, right. So, we find that delta f expression has come to this stage, and now we want to divide with delta z. Note that this is delta z, this is delta z. So, as we divide by delta z, we get delta f by delta z as this plus I into this, that is these two things, plus a lot of things from here. So, here what we will get I delta x by delta z into this whole thing, plus I delta y by delta z into this whole thing, right. Now, we want to take the limit of this as delta z tends to 0, and if that limit exists, then we will say that the function is analytic. Now, we ask this question whether that limit exists. These derivatives are all existing, that we already know. Now, note this, that as delta z tends to z, that means z tends to z plus delta z tends to z, okay, and that means that the 2 points between which we consider the line segment in which we found x1 y1 and x2 y2 as 2 points, then that means that as delta z tends to 0, this line segment shrinks, and we do not get too much space to get 2 points x1 y1 x2 y2. That means all these points shrink to xy xy itself, okay, that is z. So, that means that as z tends to as delta z tends to 0, these points have to get shrunk over a length of 0. That means these 2 points have to collapse together, and that means these will have limit 0. But what about these two fellows? Now, since delta z is delta x plus I delta y, that means if this is z and this complex number is delta z, then this length is delta z, this length is delta x, this length is delta y, right. So, delta x by delta z is cosine of this angle, and delta y by delta z in the size sense, in the absolute value sense, that is the sine of this angle. So, both cosine and sine are less than 1 in magnitude, okay. So, these two are less than 1 in magnitude. So, as delta z tends to 0, these bracketed terms will tend to 0, and these terms are bounded, that is they do not turn to infinity. If at the same time these fellows could turn to infinity, then this indeterminate form would remain. So, as delta z tends to 0, these are anyway bounded by 1, the magnitude of these two, and these approach 0, and therefore, in the limit these terms will vanish and these will remain. Okay. So, therefore, the limit exists and that limit happens to be this at x y itself. Okay. So, then whether you write it like this or you write it like this using the Cauchy-Riemann conditions, it is the same and the limit exists. So, we find that Cauchy-Riemann conditions are not only necessary, but also sufficient for analyticity. That means, the moment some function is known to be analytic, you can immediately use Cauchy-Riemann conditions. On the other hand, the moment you can establish Cauchy-Riemann conditions for a function, you can immediately conclude that the function is analytic, and all properties of analyticity you can assume immediately. Now, if we take the Cauchy-Riemann conditions, and if the function possesses second derivatives also, it will possess, because if the first order this Cauchy-Riemann condition is satisfied, then analyticity is established, and we have already discussed that an analytic function is again its derivative is also differentiable. That means, derivatives of all order will exist. So, if we differentiate this, then you find del 2u by del x square is equal to del 2v by del x del y. Similarly, del 2u by del y square is minus del 2v by del y del x. Then, from here you can also find del 2u by del x del y or del y del x as equal to del 2v by del y square, and similarly from here you get this. So, the second order derivatives will satisfy these requirements. Okay. And then you can note that if we add these two, then we get del 2u by del x square plus del 2u by del y square, and that is this plus this is 0. Similarly, if you add these two, if you add this and this, okay, if you add these two, then you will find, or subtract rather, in this case you have to subtract, from here you have to subtract this del 2v by del y square plus del 2v by del x square. Then as you subtract this minus this, you will get 0. That means, u and v, the real and imaginary components of f, in that case both will satisfy the Laplace equation, that is, both will be harmonic functions. So, this is a great property of analytic functions, that both the real and imaginary components of an analytic function satisfy the Laplace equation, that is, they are harmonic functions. And in that case, the two harmonic functions are also called the conjugate harmonic of each other, that is, conjugate harmonic of u is v. Okay. Now, we already know that families of curves, family of curves u equal to c and another family of curves v equal to k are two mutually orthogonal families of curves in the xy plane, except possibly at points where the derivative turns out to be 0. This you can see, because if you take the function u of x y equal to c, and then from there you try to find out the slope of a curve from this family, then you will consider delta u as del u by del x delta x plus del u by del y delta y, and the slope of this will be given as minus this derivative by this derivative. Similarly, if you take the family, if you take a curve from the other family v equal to k, then this will give you its slope as mk, which will be Now, if you multiply these two, you will note that del u by del x will exactly cancel with del v by del y, and del v by del x will cancel with minus del u by del y, leaving -1 in the product. In all those cases where the 4 derivatives, only 2 of which are unequal because Cauchy-Riemann conditions are satisfied, in the case that both of them are non-zero, this is obvious. Even if say one of them is 0, that is, suppose del u by del x is 0, okay. In that case this will be infinite. That means the curves of the u equal to C family will be vertical, that is, their tangents will be vertical. But in that case, if del u by del x is 0, then del v by del y is also 0. That means the slope here is 0. That means the curves of the other family are horizontal at that point. Okay, curve of the other family at that point is horizontal. So this vertical and this horizontal is again orthogonal, with respect to each other. Similarly, if del u by del y is 0, then the curve of the first family is horizontal, and correspondingly del v by del x is 0. In that case, the curve of the other family through that point is vertical, again orthogonal. The only problem will arise if both the derivatives are 0, that is, del u by del x as well as del u by del y is 0. In that case, this slope is undefined and this slope is also undefined. So it may happen that you may not be able to figure out that the product is -1 or what, and therefore we say that that kind of a situation can arise only at a point where del u by del x and del v by del x both are 0. In that case, del f by del z is actually 0, and that is what we say here, that families of curves u equal to C and v equal to k are mutually orthogonal at all points except possibly at those points where this derivative turns out to be 0.
Before proceeding further, please note this correction. The slope of the curve u of x y equal to C was written on the board as m c is equal to minus del u by del y by del u by del x. This is not right. It should be minus del u by del x by del u by del y. Similarly, the slope of the curve v of x y equal to k was written in the board as m k is equal to minus del v by del y by del v by del x. This will be corrected to minus del v by del x by del v by del y. Thank you. Now you can continue further in the rest of the lecture.
Now, a good question, a very important question is that if u of x y is given, then how to develop the complete analytic function. This is actually an exercise, the basic work regarding which we did much earlier when we were solving the first order differential equations. When we were studying first order differential equations, in that context we have actually studied this particular problem. And what we do for that is that we construct del u by del x and del u by del y from the given u, and using Cauchy-Riemann conditions we get del v by del y and del v by del x, and using del v by del x, del v by del y we construct v of x y. Okay. So, that way after constructing v of x y we get the complete analytic function. That means, if one of the components, real or imaginary, of the complex analytic function is given, then the other one can be derived using Cauchy-Riemann conditions and integration. Now,